So now let's create the big explosion. Okay, so here I've created a geometry node where I imported this explosion emitter here. I've included this explosion emitter geometry, or those explosion emitter points here in the course files, and surely I should thank the one who made this file here. I think he is called Graham Matthew, and he put it in the Vimeo description in his video, so I've used it and I've created just the geometry of the explosion. So this is okay. Let me see here. Add this frame, for example. Frame. Okay. I've added here this time shift in order to shift our simulation here, or this explosion emitter 60 frames backward here. So now if we just see here, this is our simulation, or this is not our simulation, this is our emitter of the simulation. As you can see, those points here goes up like that and fade, so I can use them as an emitter for our explosion. And this time shift here is just for adjusting the time of the emission here, or the time when the time where the points here goes up and explodes like this. So I think it was in maybe it was here in those frames. Yeah, it was here. I've shifted it forward, not backward, sorry. So I've made this time shift in order to match the time when our plane crashes with the water. So we will have explosion where the plane at the same time at the plane crash, or at the plane explosion or collision with the water. Okay, so I've made this time shift in order to match the time, and then I've created a transform node in order to transform our explosion to here, to the area where our plane collides with water. So if you can see here, let me turn off this show. Okay, so as you can see, our plane here crashes with water at this area here in frame 75 or frame 60. The plane here collides with the water, so I've created the explosion at this area. Okay, so after we just import this explosion here, or the explosion emitter here, I've added a point VOP. Let me create this. We can here create this point VOP here. Then inside this point VOP, I would just create an anti-aliased noise, or maybe a curl noise, any kind of noise that you want. And you should connect the position here at the position of the curl noise, and this will take our points positions here and create a curl or a noise based on those positions, which you can add to the velocity here. Okay, and when you add this to the velocity, you create more randomness in the emitter, or the explosion, so water will not be exploded, or will not explode uniformly. It will explode in a random way, and this resembles the nature of water more. Okay, so we will just connect this to the velocity. I think this is the first time we deal with point VOPs. I think most of you are just comfortable with this vex here, or with this vex operators, but if you don't understand this, let me explain it again. The curl noise here takes the position of our particles or our points and creates a noise based on this position. Okay, so every point has a different position, and as each point has a different position, it will have a different noise value, and you just add this noise value to the velocity here, which is the speed of our emitter or our particles, and then you connect this to the velocity again in order to change the velocity and add the noise on it. Okay, so if we just here see our point trails, which is the velocity, here is before you do the simulation, and this is before you add the noise, and this is after you add the noise. We can make this noise more stronger here, or we can change the frequency. I don't know why this mouse is not good at all, so let me create something like that. Maybe change the amplitude, maybe make the frequency higher. This will make our noise here, or our velocity, very noisy. But I have used here in this point VOP some values which you can use in your simulation, and I have this a lot of values. I've used the frequency of 6, and I have added this expression here in the offset, which is $FF over 2, and this will offset our noise and make it move as the time moves here, or as the time passes. So our noise will not be fixed, it will move each frame and change, and this will make more randomness in our explosion. So here I've added some values to the $FF in order to create more randomness. Okay, then you can replicate the points here of the emitter, or you can just use the points here as or use the same number of points here. Okay, I didn't use replicate, but the point replicate node just duplicates or replicates the points based on those parameters of the shape and the noise. This can make your simulation very thick, and this will make the explosion very thick and very strong. But I didn't love the result with the point replicate. You can try just your own result. You may want to use the point replicate, and you may love it, but I didn't love it in my simulation. So I've created a null here, which is called out emitter. This is inside the emitter node here. Inside the dot network here, let's go to the first frame. Oh my god. Inside here we can just source our emitter here beside the fluid tank simulation, and to do this we will just create a pop source node, and this can be used to source particles in a particle simulation, but it can be used with fluids without any problem. And here is the fourth tab here is called sourcing. I will connect this to the pop source. We have sourced volumes before, but now we are sourcing points, and we need to source these points each frame, so it can be here added to the initial data. This should be sourcing every frame, so we are connecting it to the sourcing tab here. So the emission type, we will select points, or we will just emit from points, because our emitter contain a number of points. So in the emitter I will just select the out emitter, and here in the burst tab you can you can just change the life of our particles, but I won't change this now. I don't want my particles of the explosion to die, so I will leave the life expectancy to 100, and the life expectancy is just the life of the particles, or how long the particles will live in seconds. So our particles will just die when 100 seconds pass. So 100 seconds is about 200 or 2400 frames, okay, because 1 second is just 24 frames. And here we will use the initial velocity, use inherited velocity, and what will this do? This will just use the velocity here, the velocity of our emitter. If we just see here, oh my god, what is happening here? It's very heavy because I'm recording. So here at the emitter geometry, if we just display the point trail, which is our velocity, we have a velocity which is let me press D and go to the visualize tab. Maybe I can add a marker here, and we will call this marker velocity, and we will call it velocity. Let me make this a vector, decrease the length scale here, and this visualizer here that I've created will just display our velocity. I've did this because point trails are just the opposite of the velocity. So when the point trails show, when the point trails here point down, this means that our velocity will point up. Instead of this confusing thing, I have made here our new visualizer, which is the velocity, and I have just entered the V attribute, which is our velocity, and reduced the length scale of our markers. It's just yellow in color. So if we just display it from here, here's our velocity here is coming up, and this is because I have used a trail node to compute velocity in the geometries that I have exported. And this geometry here that you will have in your files will have this velocity, and you don't have to create it yourself. But if you just want to create a velocity for something like this, our geometry is going up here, so its velocity will be computed showing up. Okay, so if we just add a trail node, we can add compute velocity, and in this compute velocity we can compute velocity, we will just make it central difference, and this should create here our velocity that shows up like what we did before. Okay, so here we have our velocity, and we have added the noise on the velocity, and here is our out emitter. So here in the dot network, here at this point source, we use this velocity in our simulation. So our simulation will just go up, and the explosion will be directed upwards. So this is use inherited velocity. This uses the sub velocity. Okay. Now here we have our plane collision, and we have our explosion. So now our explosion should be just emitted here in the dot network, and the simulation should work correctly. But let me reset the dot network, because I have something here, or I have pressed ESC and this stopped this forced our simulation to stop. So here now we don't have any problem or any error here at on this plane collision node here. Okay, so we have completed our simulation now, and we have the particle separation of 0.485. Now we can just do a flipbook to the simulation and see if our simulation will work correctly or not. For the test here, I can just make the start frame frame 35. I don't want to simulate the first 35 frames because the plane will not crash or will not collide with water. We need just to simulate from frame 35 for now, because this is just a test. Okay, and don't forget to unvisualize or hide the velocity visualizers here from this guy here, because if you just stay, or if you just leave the velocity visualizers here, or your simulation will crash and the viewport will be very heavy. Okay, so don't forget to turn this off and reset our simulation again, because I've pressed escape. Oh no, just return to frame 35, reset the simulation. So now we will simulate here from frame 35. Let me create a flipbook, and in this flipbook the start will be frame 35, and I will see you in the next video when we see just the result of the simulation. Thank you.